Hey everyone, in this review lesson, we're going to talk about accelerated motion in one dimension, and we're going to get into solving some kinematics problems that involve constant acceleration. So let's get started. So we teased acceleration in our last lesson, talking about acceleration was the slope of a VT graph. If we recall, slope and rate of change have connections you guys learned in your grade 9 math course. Acceleration is the rate of change of velocity. Since velocity is a vector quantity, so is acceleration. So the formula for average acceleration is the change in velocity divided by the time interval for that change. So just like we have average velocity being a change in position, displacement over time, an object's motion can be, constantly speeding up and slowing down. If it might not be possible to find an instantaneous acceleration at any given time, but if you know something's final velocity and its initial velocity, you can find what the average acceleration was, even if maybe it was changing during that interval. And again, instantaneous velocity, or acceleration, is acceleration at a particular instant. So if you recall, we talked about instantaneous velocity on a position time graph being the slope of the between 2 points. As you made those 2 points closer together, it made that time interval small. It's the same thing with instantaneous acceleration. If you look at the change in velocity over a very small time interval, you get pretty close to the instantaneous acceleration. And again, when you take calculus and vectors in grade 12, or whenever you take it, you'll learn more about this limit notation and be able to find instantaneous acceleration mathematically. But for now, this is our big one we'll be using. Average acceleration, change in velocity over a change in time. Let's actually talk about the units while we're here. Because the units of velocity are meters per second, and the units of time are seconds, we get different ways we can express acceleration. So, a couple classic ways would be, saying, hey, my object is increasing so many meters per second every second. So maybe you're familiar with writing meters per second per second. Another way to write that is meters per second squared. Maybe you're comfortable seeing that. Possibly you might be used to seeing meters seconds to the power of -2, not so commonly used. Maybe a little bit more commonly used, and I think most of us will be using meters per second squared. Now, the first notation does come in handy sometimes because it is possible to have an acceleration like, say, kilometers per hour per minute. As long as it's unit of distance per unit of time per unit of time, it's a possible unit for acceleration. But our classic one is meters per second or meters per second squared. So let's do a quick example. We have a car accelerating from rest to 96 kilometers per hour in 4.1 seconds. Let's find the average acceleration of the car. So this question doesn't exactly say units. So let's actually look at this two ways. So average acceleration is change in velocity over change in time. Let's just pop in what we have. So the change in velocity here, the final velocity is 96 kilometers per hour west, and the initial velocity is 0 because we're going from rest, I should say, in our time interval of 4.1 seconds. So if we do the math here, it's basically 96 divided by 4.1, and that gives us about 23. So we have 23, and let's think of the units, kilometers per hour per second. That's totally fine. That's a legitimate way to express average acceleration. Now, we may want to have that in a more classic meters per second per second. So alternatively, we could have converted our 96 kilometers per hour using our conversion dividing by 3.6. That is about 27 meters per second. and we could have found it this way. The average acceleration, delta v over, I might just actually do this, or delta v over delta t. We'd have 27 meters per second west minus 0 meters per second in the same time interval, 4.1. And here we'll get meters per second per second. So 27 divided by 4.1, about 6.6 meters per second, or meters per second squared. Now we'll tell you most of the time in our work, because we'll be tying in forces and energy, we'll want to be using our standard units, meters per second squared. But both of these answers would be totally valid. Now, I have a note here. When the acceleration is constant, the instantaneous acceleration will always match the average acceleration. And in cases like these, we might just refer to the acceleration. So when we do problems later on together, we'll just be saying the acceleration is this, because it's constant acceleration. Let's just make a few connections between some graphs here. So we talked about non-uniform motion in our previous lesson. So on the left here is a graph showing some non-uniform motion, and we can see, because the steepness of the curve is increasing as we proceed throughout the interval, that this object is accelerating. And specifically, it's speeding up. Accelerating can mean various things, because acceleration is a change in velocity. And an object can be moving at the same speed, but changing direction. For example, an object moving in a circle at some constant speed. It's, yes, moving at a constant speed, but since its direction is changing, its velocity is changing, and there is some acceleration there. This idea of uniform circular motion we'll discuss in a few days. But for now, we just have this speeding up, and we have some acceleration. If we look at the VT graph, so remember, velocity is like the slope of a position time graph. And if we kind of look at it, we have the slopes are kind of gradually increasing and increasing, which means we expect to see our velocity time graph, it going up and to the right as well. The velocities are increasing. It is speeding up over time. And then finally, if you took the slope of this VT graph, we talked about this but never did it, gives you the acceleration. And here we have a constant acceleration of about 4 meters per second squared. So after 1 second, our speed is, we start from rest. After 1 second, our speed is 4 meters per second. After 2 seconds, it's 8. After 3 seconds, it's 12. Every second, we are increasing our speed by 4 meters per second. Notes. So remember, the slope of a VT graph gives acceleration. And this is new. Just like there's a connection between the area under a VT graph and a change in position displacement, the area underneath an AT graph gives the change in velocity. So something to keep in mind as well. If I flip back to our previous question here, the area underneath this curve is actually pretty straightforward. It's a rectangle with a height of 4 and a base of 8. 4 times 8 is 32. And we can see that after 8 seconds, our speed is 32 meters per second. We've gone from 0 to 32, a change of 32 meters per second to the east. All right, we've hit those notes. So we've talked about now position, displacement, velocity, acceleration, all those terminologies for motion from grade 11. And now let's solve some problems. The equations governing motion in one dimension are often referred to the Big Five. The Big Five, because we generally have like 5 variables for our motion in one direction: acceleration, final velocity, initial velocity, displacement, and time. And kind of each one of these equations kind of eliminates one of them. So, if I was doing a problem where I was given, say, 3 of the first things: acceleration, final speed, initial speed, or velocity, and time, and I was asked to find a 4th one, I would use, this general equation. And so where these come from, you guys derive these in your grade 11 course. This first equation here is just the definition. Blue's not really showing up too well there. This is just the definition of acceleration. So these are just my names for them. Definition of acceleration. The second one I call the displacement curve equation. The third equation here is just the definition of average acceleration or average velocity. It's just the definition of average velocity. The fourth equation, because time is limited, I just call it the timeless equation. This is just my name for it. And the last one, it's just a displacement curve, just a different version of it. So I just call it the displacement curve 2. Displacement curve 2.0. Whether you have names for them or not, that's okay. Now I do want to mention too, different teachers, might use different versions of these. Here's the versions I use. You'll notice I've dropped the vector signs. When we're working in one dimension, the direction can be assigned to any of these variables with a positive sign or a negative sign. So when working in one dimension, it's okay for us to drop those vector signs. It can actually make it a bit more convenient for us. That's why I've dropped these here. That's why you don't see them. This is for one dimension. And the equations may look a little bit different. For example, this first one is my average velocity equation. You can see that one shows up in the third one on this page here. But they're the same equation, just average velocity, just in a different form. And then I have my definition of acceleration just rearranged for this kind of, for most of you, this will be the classic way you've seen this equation, v2 equals v1 plus a delta t. If you rearrange that, subtract v1, divide by delta t, you just have the definition for average acceleration. Of course, here we're talking about constant acceleration. So we just say a, the acceleration. Displacement curve 1, displacement curve 2, and the timeless equation. So what we want to do now is get a bit of review practice using the big 5, using these governing equations for motion in one dimension. So let's do it. So you guys, again, coming from different backgrounds, different teachers, everybody has their own little way that they're comfortable solving problems like these. So if you don't like to set them up kind of like me, that's okay. So here we have a motorcycle traveling at 12 meters per second west. So I'm just going to make a little sign convention here. This is how I prefer to do these kind of questions. So I'm going to, so if north is that way, west is this way, and I'm going to just make a little convention here. I'm going to say to the west is positive. Some of you guys may like to use the grass method of doing a solution. So this is the one time I will kind of write out what those words mean. And then you can just, do these problems however you're comfortable, as long as you really show your work. But the first thing would be kind of like, well, let's write out what we're given, right? We're given initially, we're traveling at 12 meters per second west. So V1, and I chose, so you could write 12 meters per second west, but I've chosen west to be positive. So I can just write 12 meters per second, the positive indicating it's west. It changes gears and speeds up for 3.5 seconds. That's a time. Delta t equals 3.5 seconds. With a constant acceleration, so a, 5.1 meters per second west. So it's in the west direction, so it can use positive 5.1. What is the motorcycle's displacement? Looking for delta d. And again, it's in one dimension. I've dropped all the vector signs because it's either west or east, positive or negative. I may be able to squeeze this in here. I may be able to squeeze it below. But first, we figured out what's given, and then what's required. Required, we're finding this displacement. And the next step would be analysis. So thinking about, hey, which of our governing equations would help us here? Maybe if you want to pause the video and just check out which of those would help us, and unpause when you're ready. But with the 4 we have and the one we're trying to find, or the 3 we have when we're trying to find, it's the displacement curve equation that will help us. V1 delta t plus 1/2 a delta t squared. We have all those things on the right. We're actually just ready to calculate the displacement right away. So V1, and so that's our analysis, is kind of thinking about what math tool, what equation will help us solve the problem. And now we're into our solution, where we'll actually, plug in our values, work this out. So we have 12 times 3.5 plus 1/2. Our acceleration is 5.1, and our time 3.5 squared. Now, this can be all done at once. You could do it in 2 steps if you'd like, but I mean, our calculators have no problems doing strings of addition, multiplication. So I'll just do that. Times 3.5 squared. All right, so I got a displacement of about 73 meters. So let's make a statement. The displacement is 73 meters. And remember, displacement is a vector, right? Has magnitude and direction. So for those of you freaking out that I didn't have a direction here, we'll take care of this in the statement. It's positive. My sign convention was west is positive, so the displacement is 73 meters to the west. So we've solved this problem. And we've kind of solved it using the GRASS method: given, required, analysis, solution, and statement. Now, if you don't prefer to lay it out this way, that's okay. Do it the way you're comfortable. If you like to include the units, please do that. But I think this is a reasonable solution. But again, you do not have to do things my way. If you're showing your work, that's great. And this just gives a structure for those of you who just need something to start. So let's try another example. Maybe use a different Big Five equation. So here in this example, we're actually talking about a projectile, but one that's launched straight up, so launched vertically. So we have a rocket launched vertically from rest. So I'm not going to write out given required here, but this is just how I generally like to do these problems. So from rest, so that's a big clue that V1 is 0 meters per second. It reaches a final velocity of 6.3 times 10 to the 2, so 630 meters per second up. So at this point, I might want to do a sign convention. So if I have my rocket blasting up, little cloud, we have a choice. For this one, I just might choose up to be positive, just because. So having chosen up to be positive, it reaches a velocity of, and since it's moving up, that's 630 meters per second. If I had chosen down to be positive, then I would be using negative 630 meters per second. All right, and we also have that this reached an altitude, reached the speed at an altitude of 4.7 kilometers above the launch pad. So above the launch pad, so our displacement is 4.7 kilometers up, or positive 4.7 kilometers. Let's get that in meters, 4,700 meters. And what do we ask for? We're asked for the acceleration. All right, so let's proceed to the analysis. We need to choose an equation that'll help us solve this. So if you want to take a moment and try to find one that'll work. The fact that we do not have time leads us to think we need to use the timeless equation. V2 squared equals V1 squared plus 2a delta d. It has everything we need. Now, my preference, if I'm solving for a, I like to just rearrange for a. So I'm going to do that now. And for most of us, the level of math we've done, this shouldn't be too onerous of rearranging a formula. We're going to bring the V1 squared over by subtracting it. And then to get A by itself, we would need to divide by 2 delta D. And we're ready to go. So V2 squared, so 630 squared minus 0 squared, all over 2 times 4,700. Now, I'm going to do this all at once on my calculator, but do it in a couple steps if that's what makes you feel comfortable. I got an acceleration of about, just keeping the sig figs the same, about 42 meters per second squared, or meters per second per second. And we'll make a little statement. The acceleration is 42 meters per second squared, and the direction up, according to my sign convention. All right, so another one in the books, just giving you some kind of structure for how to do your solutions as well. But again, if you had your way of doing things from grade 11, please keep that up. If you're more comfortable keeping the units in, I was careful to make sure I was using consistent units, so I know my final units for acceleration would be meters per second squared. I like using a sign convention for the direction I'm moving in. I chose up to be positive. My final answer was positive, so I know the acceleration is up. But again, one last time, do what makes you feel comfortable. If you're showing your work, that's good with me. Let's do one last example together. Here, Asher throws a stone straight down from a bridge. The bridge is 15 meters above the water, which with an initial speed of 4 meters per second, and he's throwing it straight down. So if you can imagine, maybe make a little visual of this to the side. Got little Asher up on a bridge. There's a railing, don't worry, and we have the water below. So he fires his stone down, like so. Let's write out what we're given. So Asher throws a stone straight down from a bridge, 15 meters above the water. So we have a choice. The stone is moving downwards towards the water. Do you want to choose down to be positive, or do you want to choose up to be positive? It doesn't matter. I'm going to choose up to be positive, just because. So the stone, its change in position as it goes from the bridge down to the water, delta D, it's moving in the downward direction. Its displacement, if I choose up to be positive, will be negative 15 meters. 15 meters in the negative direction. Initial speed of 4 meters per second, and he threw it down. So I know that my V1 will be minus 4 meters per second. We're asked to find delta T. And we need one more thing. And in this question, we're going to be making use of, in this case, and you will learn in grade 11, here the acceleration, once it leaves Asher's hand, the acceleration of this object, this stone, is the acceleration due to gravity. So the acceleration due to gravity will be straight down towards the water. So we will use minus 9.8 meters per second squared. Now, alternatively, if you chose the downward direction to be positive, then all these things would be the same numerical value. They would just be positive. We have there's two ways we can do a problem like this for finding delta T. The first one is, well, if we look at the four things involved here, the 3 we're given, the 1 we're not, the displacement curve is the equation that has those 4 things, V1 delta T plus 1/2 A delta T squared. But what you'll notice is there's no way to isolate for delta T. It's a quadratic equation. So if we plug in what we have, negative 15 was negative 4 delta T, a half of negative 9.8 would be negative 4.9. We get this quadratic equation. And to solve it, a bit of grade 10 math review, we need everything to be on one side. I'm going to choose to put things on the left. I just have more things being positive. So 4.9 delta t squared plus 4 delta t minus 15 equals 0. So you in your grade 10 math course, you learned 2 ways to solve quadratic equations. One is using factoring, which this one would not be practical to factor. The second is to use a quadratic formula. So let's set this up. So I believe in your math skills diagnostic, I had you guys practice a couple of quadratic formulas. So I'm going to, assume we're fairly proficient using that. We have the quadratic formula is negative b, so the opposite of our delta t term, so negative 4. We get 2 solutions, plus or minus the square root of. Inside that root, we have the discriminants, b squared, 4 squared, minus 4 times a times c. A is 4.9. C is negative 15. Don't forget that. Keep the sign as well. All over 2 times a, 2 times 4.9. So this is going to spit out 2 times for us. So let's see if both are meaningful or if only one is, and which one is and which one's not. So I'm just going to take a moment and hammer this out. You know what I might do actually? Let's do an intermediate step, and let's calculate the discriminant first. Do the bottom, that would be 9.8. So 16, it's going to wind up being plus 4 times 4.9 times 15. So we get 310 under the root. And now I'll get my 2 solutions. So I'll just say delta t1 comes from doing the top, negative 4 plus the root of 310 divided by 9.8. So I got about 1.4 seconds. And delta t2, I'll get using subtraction, negative 4, negative 4 minus root of 310, and divided by 9.8, negative 2.2. All right, so which makes sense for a time? Well, this first one, the time interval that gives us a positive value makes sense, 1.4. So make a final statement. It takes 1.4 seconds for the stone to hit. So it wasn't too bad. We could just use the displacement curve equation and use the quadratic formula. Now there is an alternative. If you're not a fan of solving quadratic equations, we could find the final velocity first. And what I'd actually like to do is I'd actually just like to switch the problem up. Let's have some fun here. And let's just actually, so Asher's throwing the stone down. Let's actually just choose down to be positive for this one. So same setup here. So V1, Asher's throwing it down. So let's use full positive 4 meters per second. Acceleration due to gravity would be positive 9.8 meters per second squared. The change in the stone's position is in the downward direction, positive 15 meters. And we're asked to find delta t. Now, this question does not involve V2. We're not asked to find it. There's nothing saying that we can't find it. So in this question, we're actually going to find the final velocity and use that to get the final time. And so we can get that by using the timeless equation. V2 squared equals V1 squared plus 2a delta d. Now, what we have to be careful of is the fact that there's 2 possibilities here. To get V2 by itself, you take a square root, but it could be the positive of the value you get or the negative. So I'll ask you, maybe pause the video and think. Considering the problem, with the sign we've chosen to be the positive direction, which direction we've chosen to be positive, excuse me, and considering Asher throwing the stone and what its velocity will be when it hits the water, will we be taking the positive value of this or the negative value of this? If you said we'll be taking the positive value, you'd be right, because when the stone hits the water, it'll be moving in the positive direction that we've assigned. So let's crank this out now. So it'll be positive 4 squared plus 2 times 9.8 times 15. And let's just do this all in one step. So we have 16 plus 2 times 9.8 times 15. We get 310. If we root that, we get about, I'm just going to keep a bit of accuracy here. So 17.6 meters per second when it hits the water. And now that we know V2, we actually have a lot of possibilities for finding time. We can use a lot of different equations. And if you didn't want to solve a quadratic equation, you might be able to use this one. V2 equals V1 plus A delta T, because now we know V2, V1, and A. So we can find delta T by solving for this, V2 minus V1 divided by A, 17.6, roughly, minus 4 divided by the acceleration, which is 9.8. So one thing to keep in mind is we did round to get this V2, where in our quadratic formula, we did less rounding. So our answers should match up pretty well, but they could be slightly off depending on the method we chose. By 9.8. Yeah, I've got the same answer. At least to 2 sig figs, I got the same answer, 1.4 seconds. In practice, one is no better than the other. The advantage to the previous method is that it solves it fairly directly, just one equation. The advantage to the second method is there's no quadratic equation. However, you do have to be careful when finding V2 to choose the appropriate sign using the context of the problem. So here we knew that the stone would be moving downwards, the positive direction, 17.6. All right, guys. So we've done 3 examples of using the Big Five, reviewing the 2 methods you have to solve for delta T, either using a quadratic equation or by finding V2 first. The rest is up to you guys to practice a bit. That's all been posted. I'll end the video here. Next, we're going to review some vector concepts, like how to add vectors, how to add vectors using components, and then apply what we know to projectile motion, which will be review for many of you, maybe not for some of you, but that does involve, it's a nice way to tie in kinematics and vectors together. That's it for today, guys. Hope you're staying well. Have a great day. We'll see you soon.